Okay. Let's see. There's nobody left here in person. And Brittany was here earlier and you got a copy of everything. But for Heather, for the review document, there may be more than one copy in Brightspace. So we're going to focus on this one, which is version 2. Right there. And the review work problems for version 2 are not in Brightspace yet. I just completed them and made copies for people who showed up, but they'll be probably by Wednesday. I'll have those in Brightspace. And then we have one, since there's only one chapter in this exam, we have one of these crossword puzzles. And then next week, we're going to do this lab, which is chemical kinetics. And the version is February 23. So if you see an earlier version, let me know, because it's supposed to be this later version. All right. So let's talk about chemical kinetics. Get that out of the way. Go. Let's see. We've got until 12:20. So that gives me 2 hours to cover this material. I think I can do it. But if I do, there won't be enough time to talk about the lab. So what you'll have to do is go into Brightspace, and there are several lab discussions in there. Go to the most recent one first and get some background on this lab exercise. All right, chemical kinetics, chapter 12. When we talk about chemical kinetics, we are discussing the rate of reaction. How fast is the reaction going? We're not saying anything about whether it prefers to be one side or the other. I mean, is it going to end up over here, or is it going to mostly end up over here? We're not saying anything about that. We're saying, how fast does it go from here to here? No matter what the outcome is, we want the speed of the reaction. And we express that as a rate in terms of, for the initial purpose, the very simplest purpose, we're going to say A becomes product. We're going to just a single reactant. Now, we know that a lot of reactions need more than one reactant, but when we start studying kinetics, we have to keep it simple at the beginning to get a firm grasp of the concepts, and then we'll advance to more complicated reactions. But in this case, we're looking at this rate as a change in concentration. This is always expressed in terms of concentration, not total amounts, concentration of A. And if we consider the concentration of A at some final point, and then the concentration of A that we started with, or we might put an I in there for initial, and then the amount of time it takes to go from one to the other. So the final time minus the initial time, that gives us an idea of the disappearance of A, because we're going to find this concentration is less than that one. It would give us a negative number. So that's the generic expression for reaction rates. And when we put a square bracket around our component here, we mean concentration in molarity. Now, we don't always have to use that, but that's where we start. We start discussing concentration changes in terms of molarity. Another possibility is later if we discuss a reaction in terms of, and all the components are gases, then we can discuss this concentration in terms of partial pressure. All right, we learned about partial pressures last semester when we talked about gases and and we express their concentrations in terms of pounds per square inch or atmospheres or whatever the case may be. But for now, we're going to keep it simple. We're going to speak in terms of molarity. And that's what the square bracket means. This is a set of sample data, comes straight out of your textbook. And the reaction is of the balanced equation for the reaction is nitrogen dioxide becomes nitrogen monoxide plus oxygen. These are all gases. Let's see, we need a 2 here. And the condition for the reaction is that it occurs at 300 degrees Celsius. Okay, so we're getting a decomposition here. And the data set tells us that we're measuring concentrations of the reactants and products every 50 seconds. All right, so we get a list, and we start off with at time 0. Let's do it this way. We'll use this as our heading. For time 0, then we have 0.010, another one, molar. And at time 0, we have no products. All right, so after the first 50 seconds, we end up with 0.0079 molar nitrogen dioxide and 0.0021 here and 0.0011 there, all in molarity. Okay, I'm only going to look at this part of the table because we can see that the stoichiometry is correct. In other words, if we go from here to here, what kind of change is that? We just subtract the 2. 1, 7 minus 2, 0, 0.0. So we've had a change of 0.0021 molar. Where did that go? It went to product. So this amount went from here to here. And notice the ratio here is 2 to 2 or 1 to 1. So if this disappeared from here, it had to show up over here. And sure enough, it did. We measured it as 0.0021 molar, which came from here. The stoichiometry also says that for every 2 of these, you get 1 of those. So this should be half of that value. And it is. So we're not saying that the stoichiometry is thrown out the window. It's just that the reaction rate obeys the stoichiometry overall. And we can deduce that from the data. That's just comforting to know that kinetics doesn't negate anything about what we've learned so far. Right? And you can make these measurements over time. And one thing that happens though, and we'll study this in more detail next chapter, is once you start building up product, then you can have a return reaction. It can go the other direction. Right? So that interferes with understanding the rate of the reaction in this direction. Because once you start getting a return reaction, you don't convert all this to that. So many times we investigate these reactions in terms of the initial rate. That is, what's the instantaneous rate at the very beginning when the return reaction is inconsequential. Right, we'll have examples of that in just a few minutes. This is a graphical representation of what we see here. And what we've got on the y-axis is simply concentrations of the components and time on the x-axis. So you notice that up here at the top, this is all nitrogen dioxide. And there are none of the products measured in concentration. So as this one decreases, these increase. And notice that the rate of increase here is the same as the rate of decrease because the stoichiometry says they're 1-to-1. Whereas the rate of increase of oxygen is only half as fast because of the stoichiometry is 2-to-1. What you'll also see on this graph is that the progression of the reaction is a curve. So if we want to know the rate of the reaction, change in concentration for change in time, in this case, it would be change in concentration of NO2 or a change in time, then the only way to determine that value is a method called instantaneous rate. In other words, we can't just take 2 points on that curve and do our typical y2 minus y1 over x2 minus x1. It doesn't work that way because we've got a curve. But if we take a tangent to that line, if you have a curve, right, and you take a tangent to that line, that's not a good, say right here, then the instantaneous rate at that point on the curve is the slope of that line. All right. So what you notice from here is that the rate of the reaction is decreasing over time. All right. Okay, so back to this equation again. Every balanced equation reaction can be described in terms of its kinetics using a rate law. And the rate law with respect to this component would be the rate equals some constant times the concentration of NO2 to some power. Right? This is a constant. And this power is known as the order of the reaction, of the order of this component. This is equal to the order. Now we're going to study it in terms of whole numbers for N. But as a practical matter, when you start working with chemical kinetics, this value does not have to be a whole number. It's just easier to understand if we look at the whole number examples first. Right? Because reaction rates, this law has to be empirically determined. In other words, it bears no resemblance in any way to the balanced equation and the coefficients that we insert there. You can't deduce any of these values from this reaction. Not as written. It has to be empirically determined. Now, we're going to introduce some ideas later on that help us toward that understanding, but we're not there yet. Okay. Notice that in this case, we're not interested in the products. We're gauging the rate based upon the disappearance of the reactant. And we're doing that because we're studying this reaction under conditions where the return rate from these products back to the reactants are minimized. So we're at a condition called initial rates. And I said that before. Those values have to be empirically determined. All right, this expression of the rate law, they won't have that there. This expression is called the differential rate law. Now, these descriptive terms are derived from calculus, but you don't have to know calculus to get this part. This expression, this differential expression, shows how the rate of the reaction depends on concentration only. Because you determine this from the experimentally, and this is a constant, so the rate is dependent upon the concentration. But that's not always the best way to approach it. So what we've done is derived an integrated rate law. And these two rate laws are related to one another. So if you know one, you can deduce the other one. Right? Sometimes it's easier to approach it from this side rather than that side. The integrated rate law actually shows how the concentrations of the species in the reaction depend on time. And there are different rate laws here depending on what that value is right there. All right, so we're going to take those one at a time. I've already said those things, so I just leave them up there so that they're recorded. That first statement is true. Experimental convenience usually dictates which one of these we use when evaluating the kinetics of a chemical reaction. Now we're going to get into it just a little bit later, but I'll make this point now. This is what's known as the overall reaction. In other words, it's what we see happening. We see reactants go in and products come out. But we know from experience and from lots of experiments that there's a lot of stuff happening right there. And most reactions occur in 2 or more steps, elementary reaction steps that together yield this overall reaction. Okay? And by studying what we can about those individual steps, hold on a second. There. By studying these individual steps and teasing out that information from our experiments, we're able to learn more about the reaction rate and how it develops, and which one of the rate laws is actually the right one for that reaction. All right, so we're going to determine experimentally the power to which each reactant concentration must be raised. So if we have multiple, let's see, more to this slide. No. If we have multiple reactants, say we have a reactant A plus B yields products. then we would write a rate law for both of those reactants. We still have a constant, just one constant. Then we'd have the concentration of A raised to its order and the concentration of B raised to its order. A different value. Could be the same, could be different. But that's how we would express the rate law for more than one reactant. All right, so this method of initial rates is simple. We measure the rate of the reaction at the very beginning. Very near to time zero. It can't be time zero because some time has to pass in order to measure a change in concentration. But we make that time period as short as possible so that the reverse reaction does not interfere with the measurement of the forward reaction. And one of the ways we do that is we conduct several experiments using different concentrations. Now, the choice of those concentrations is very important. An example would probably explain it better than just giving you a wordy description. Right, so there's one. There's the example that I wrote here. Now, N would be the order of this reaction with respect to A, and M would be the order of the reaction with respect to B. The overall order equals N plus M. Or if we have more than one, if we have several out here, just add them all together. And if the question is, what's the overall reaction order? Just add them together. So if this one were 1 and that were 2, the overall would be 3. All right, just to check, how do exponents, the orders of the rate law compared to coefficients in the balanced equation? They don't. They're not related. Not in the overall reaction. What we're going to find out is when we develop these elementary steps that are occurring here, then we can use the coefficients of the elementary steps in developing the individual step rate laws. Right, but that'll come later. Right, this balanced equation is an expression of stoichiometry. It actually says nothing about kinetics. All right, so we're going to study 3 different types of reaction based upon their order. And we're going to keep it really simple. We're interested in one reactant and one order at a time. So we're going to have 0 order where the N is equal to 0. We're going to have first order where N is equal to 1 and second order where N is equal to 2. We're going to characterize those reactions with respect to their kinetics. Right, so the 0 order reaction would be written this way. The differential rate law would be this one, K times whatever A happens to be to the 0 power. Okay, which means that it's actually equal to K because anything to the 0 power is 1. What that means is that the rate does not depend on the concentration of the reactant. The rate's the same no matter what the concentration is. All right. This was the differential rate law. The integrated rate law is A, the concentration at any time t is equal to, negative K times T plus the initial concentration of A. So this means that's our starting point, and this is what the concentration at time T. Okay. So what that means in practical terms, and the integrated rate law is very useful if we want to plot concentration versus time. This place right here, notice this is y equals mx plus b, a straight line. So if you plot this data, if you plot your data, concentration versus time, then you will get a straight line if it's zero order. Right? You get a straight line like that. And the slope is going to be minus k. Okay? And of course, that slope is going to be equal to a over time t, or delta a over time t. Okay? That's where the integrated rate law is very useful, because the integrated rate laws are set up to be straight line expressions. Okay, there's one other bit of information that we can get from this data, and that's the half-life. You may have heard discussion of half-life in terms of radioactivity, right? So if you start off with a certain amount of radioactive material, after a certain amount of time, only half of it is left. The other is changed into something else. Well, we can speak of half-life in terms of chemistry too. So how long does it take for this initial concentration to drop to 1/2 of its initial value? That's the half-life. So the half-life is an expression of initial concentration and its relationship to the constant. Okay, so half-life is related to the initial concentration and to the constant, the rate constant. All right. So what does that mean? Well, that says that the half-life changes with respect to the concentration of A. So if we take an initial concentration at actually time 0, then after a certain amount of time, there's a half of it left. But if we start off with a different amount of A, say we work our way down through the experiment to a different point and say, all right, what's the half-life from here to the next step? Then because this value changes, as this decreases, then the half-life decreases over time. All right. This is just interesting, right? We take the integrated rate law and derive the half-life from it, right? I'm not going to have you do this. I just thought it was, it was an interesting exercise. We're just saying that the half-life is, what's the concentration? If you start off with this amount and take half of it, how long does it take to get there? And then what you can do is substitute this value, A0 over 2, into this position over here, and then solve for the half-life, because T now is T 1/2. It's very simple algebra. All right, next, first order. That would be an expression where rate equals K times the concentration of A to the first power. Okay, you don't have to write the 1 up there. In fact, we usually don't. Right? It's understood. So how do we get a straight line out of this data? If you plot first order data like we did over here, you'll get a curve, right? That's no good. We need a straight line. So the integrated rate law says that the natural log of A is equal to minus KT plus the natural log of A0. So that says if you plot the natural log of A, then instead of a curve, you get a straight line. All right. Here's an example. And the y-intercept, of course, is this value, the natural log of A0. And the slope is minus K. But the slope is the change in the natural log of A over change in time. Right? So if you want to use this straight line information to derive or answer a question, say at what time, what's the value of concentration of A at time T? So if you pick this time out here and you go up here like that, you go across here, your value is going to be the natural log of A. If you want to find out what A actually is, then you take the inverse of the log, e to the x. So you take that value and put it in as a power of x of e, and then solve it for that. The anti-log is what I was looking for. But this will give you a straight line if the reaction is first order with respect to A. Now we have half-life possibility. What's the half-life in this case? Is equal to 0.693 divided by K. So in this case, we see that the half-life does not depend upon the concentration of A. It doesn't depend on the concentration of the reactant. Whereas at any time in the reaction, the half-life is going to be the same everywhere for every time interval. All right. Now the next one and the last one we're going to study. There's the derivation. Right. You can do that if you want to. If you like math, it's fun. Let's see. Okay, before we go to second order, we're going to take this little problem and use our information from the first order to derive K. First order reaction, 35% complete at the end of 55 minutes. So if we set up our table for these concentrations, then we find that after 55 minutes, we have used up 35%. And so we have a value here of X, and after 55 minutes, how much do we have left? Well, the reaction is 35% complete. That means we have 65% left. So this value is going to be 0.65 of X at the end of 55 minutes. We want to find out what K is. Well, this takes a little math, and we know it's first order, so we're using this integrated rate law because we have time and concentration together. That's why we use this one, not that one. That one doesn't have time in it. This one does have time. So if we use that reaction and we solve this equation for the ratio of A to A0, right? So this is equal to A0, and this is equal to A at 55 minutes. We want those ratios in there because the ratio is going to be 0.65. So we solve our equation for the ratio of A to A0, and we end up with this expression. A to A0 is equal to E to the minus KT. Right? Now we know what that ratio is. It's 65% or 0.65. Okay. The ratio of A to A0, this one to that one is 0.65. So if we plug that into the equation along with the time, okay, so we have 0.65 here, and this is E to the minus K times 55. Now we have an equation in one unknown. We just have to solve for K. So how do we do it? We'll take the natural log of both sides. Remember, the natural log of E to a power is the power, because the base of the natural log is E. Right? So we're going to take the natural log of both sides. And what we end up with is natural log of 0.65 equals minus K times 55. Okay, so we just take the natural log of that, divide by 55, and change the sign. And we end up with 7.8 times 10 to the minus 3 reciprocal minutes. So K is equal to 7.88 times 10 to the minus 3 reciprocal minutes. Oops, I put to the only 1/8. There we go. All right, second order. I have to erase this now. Make room for second order. Oops. Let's write it out. Okay. Second order would be rate equals K times A to the second power. For this one, the linear expression comes out as the inverse of A equals KT plus the inverse of the initial concentration. Okay, so what that means is if you have a second order equation and you plot time against the inverse of the concentration of A, then you'll get a straight line. There's time, and there's inverse of A. And notice now the slope is positive. Okay, and this one, this point right here is 1 over A 0. And this slope, K equals the slope of the line. All right. So on the left, what we're illustrating here is for this particular reaction where C4H6 decomposes, if we plot it in either of these formats, if we plot the raw data or if we plot the natural log of C4H6 against time, we get curves, right? So we know it's not either one of those. But if we plot it as the reciprocal of C4H6, then we get a straight line. That tells us that our data says this is a second order reaction with respect to C4H6. All right, now we have a half-life here also. Probably on the next page. Yep. This is, the half-life is 1 over K times the initial. So we also find out that the half-life here depends on the concentration of A. And over here, it depends on the concentration of A. But in this case, as the concentration of A decreases over time, the half-life decreases. But in this case, as A decreases, the half-life increases. All right. Let's separate those. All right, those are zero order, first order, and second order reactions. And we're studying these as whole number values for the order because it's easier to get a grasp on it right now. And this is the derivation of the half-life for a second order. All right. So let's see, I didn't leave myself much room, did I? For the reaction of A yields products, if A0 equals 5 molar and the first two half-lives are 25 and 50, respectively, write the rate law, calculate K, and calculate A at the end of 525 minutes. Okay, first thing we have to do is find out what's the order of this reaction. All right, I'm going to have to erase this so I can write on the board. This may be enough room right here. Okay, what are we given? Well, we're given that A yields products. Okay. We're also given initial concentration of A was 5 molar. So at time 0, the concentration is 5 molar. Okay. The first half-life is 25 minutes. So after 25 minutes, what's the concentration of A? It's half. After that amount of time, it's half. 2.5 molar. And then the second half-life is 50 minutes. So if we start from this point and take another half-life, now this one's going to be 1.25 molar. But the overall time is 75 minutes. Okay. All right. So the approach to this is, since we're given half-life data, look at the half-lives. Notice, first of all, that the half-life changes from 25 to 50, depending on the initial concentration. So, which one of these doesn't depend on the concentration? This one. That means this data cannot come from a first-order reaction. These values should be exactly the same if it were first order. So now all we have to do is decide, is it 0 or second order? Okay, so if we take the 0 order expression, T1 half equals K over 2A. I believe that's right. Here we go. That's the statement I just gave you. We can eliminate first order. Oops. Did I do them wrong? Yeah, I did it wrong. 0 order. Over 2K. There we go. So in this case, if we put in the values of time, first half-life is 25, and we're starting from 5, then what would be the K? We solve for the K. And the K in that case would be 0.1 for this one. Right? What would it be if we put in 50 minutes, starting was 2.5 molar? In that case, we'd get a K of 0. For this one, we get K equal to 0.025. All right, what's wrong with this picture? K is a constant. If we don't get a constant value from this calculation, that means it cannot be 0 order. So by deduction, right, process of elimination, second order has to be it. But we're going to prove it anyway. All right, so if we do the same calculations for second order, right, then we get K equals 1 divided by 125, or 8 times 10 to the minus 3 in both cases. So our constant is the same for both. That means K is 8 times 10 to the minus 3. All right, so let's see. K. So the reaction is second order with K equals 8 times 10 to the minus 3. All right, we know that now. So the rate law would be rate equals K, or that value. Let's put the value there. 8 times 10 to the minus 3 times the concentration of A to the second power. Right, that would be the rate law. After 525 minutes, how would you calculate that? Well, we take this equation and you say this value is 525 minutes. This value is 8 times 10 to the minus 3. The initial value is 5, and solve for A. Okay, and there it is. A now, after 525 minutes, is 0.23 molar. All right. And there it is on one page. So how do we tell the difference among zero, first, and second order rate laws from their graphs? Well, obviously, and I've said it before, but I'll say it again. Let's see. Yeah, next slide. No. I guess I have to explain it again. Take your raw data and plot it. Time against the concentration of A. If you get a straight line, it's zero order. If you get a curve, then go to the next one, first order. Take the natural log of A and plot natural log against temperature. Time. Natural log against time. If you get a straight line, then it's first order. If you still get a curve, then go to the reciprocal. Plot the reciprocal data, and that should give you a straight line. So, as a practical matter, if we want to determine what the order of a reaction is, set up an Excel spreadsheet with time, the concentration of A, and then have your spreadsheet calculate natural log in the next column and reciprocal in the next column. And then you can go in and pick out your columns to have the data plotted by Excel. And it will tell you which one is a straight line. If you're not comfortable doing that with Excel, you can still do it by hand. It just takes longer. So what do we do in the case where we have two reactants? Right? If we have A plus B yields products. Well, you do what we're going to do next week in our kinetics experiment. What you do is you take one of them, and I'm just going to arbitrarily pick this one. Right? You increase the concentration of B so that it doesn't change during the reaction. You increase this concentration so high that it does not change during the reaction. Right? In that case, then we're starting off with a rate law like this. Equals K times A to the N and B to the M. Then if you increase this one, if you increase B to a point where it doesn't change significantly during the experiment. Now what you have is a constant value here, and this is constant also. Right? So these two combine into a K prime, which is equal to K times B to the M. Now we write the rate law this way. Rate equals K prime times A to the M. Right? Now we conduct our experiment on this one first and determine what order it is. We find out this one from that data. There we go. Man, that's as far as I've gotten so far. Oh, and we're saving the complete discussion for the discussion of the lab. All right, like I said at the very beginning, we're probably not going to have time to do a special discussion for this semester. You'll have to go and look at historical discussions, and they cover this information in reasonable detail. And get your information from those recordings in Brightspace. So then what do? Well, I'll just give you a teaser. Then you change the concentration of B and you get a different B value. Right? So in that case, you get this one at full strength B, and then what we're going to do is change the concentration of this one to half strength. And then you get another K prime half strength. Okay? Then we ratio the two. And that's as far as I'm going to go right now. Okay, this came straight out of your book, and this is a compilation of everything we've discussed so far about zero, first, and second order reactions. All right. What I'm trying to impress upon you in this slide is the difference that the order makes in the actual reaction rates. So if we have this example where we have A0 is at a concentration of 5 molar. And we allow the reaction to proceed for 30 seconds. And we have the K value given as 1 times 10 to the minus 2. All those are given facts. What we are changing is the order of the reaction. What is the outcome after 30 seconds with an initial concentration of 5 molar and a K of 1 times 10 to the minus 2? We'll calculate each one of these for the zero, first, and second order situations and see what effect that has on the final concentration of A. I think you can intuitively predict that zero order is going to run slower. First order is going to run faster. Second order is going to run even faster. So that means that after the same amount of time, we should have a certain amount from zero order, less from first order, and even less from second order. But this is the mathematical proof. Right? So there we have the zero order equation. We insert the K value. We insert the time value. We insert the initial concentration and calculate the final concentration at 4.7 molar. Then we'll do the same thing for first order. It's a different equation, but the same values of A0 and K and time. And we end up with A equals 3.7 molar. We'll do the same thing for second order. All right? Plug those values in, and A now is 2 molar at the end of 30 seconds. So that bears out our intuition that the higher the order, the less you have left at the same after the same amount of time. All right, now we're going to talk about the method of initial rates. Right? It's not complicated, but you have to be organized. And the experiment must be set up properly so that you can use the data to answer the questions. So here's our example. This example reaction. Let's see. I'm going to spread it out because I'm going to use the equation as a header to put the data underneath. So 2MnO4 minus and 2, and 4 plus 5 C2H2O4 and then 6H plus, and that yields product. We don't care about the product because this is initial rates. We only care about the reactants. Okay. All right. So here's the data. What we've got here is 4 separate experiments. And we determine the initial rate of each experiment with those concentrations. So for the experiment 1, okay, we have a concentration of 1 times 10 to the minus 3. For the manganate ion, we have 1 times 10 to the minus 3 for the oxalate ion, and we have 1 molar for acidity, protons, hydrogen ions. And the rate comes out for this initial rate for this concentration of each at 2 times 10 to the minus 4. Okay. Now we have three more experiments. Notice that this one stays the same for the rest of them. And for the oxalate, we also stay the same. For the first 2. And then for the second 2, we allow it to change. And then for the last one, these are the same, and this one is allowed to change 2. Now the rates for each one, 8 times 10 to the minus 4. Okay. 1.6 times 10 to the minus 3. And 1.6 times 10 to the minus 3. Okay. Notice what we've got here. The difference between this one and this one is a change in the manganate. These two do not change. And then the difference between these two is that manganate stays the same, hydrogen ion stays the same, and we allow oxalate to change. And then for the last one, the manganate and the oxalate don't change, but the hydrogen ions change. That's the way we set up our experiments so that we can ratio any 2 of these to observe the change in the third one. All right, so what we need is a rate law to go by. So the rate law here is going to be, let's see, I'm going to run out of room. The rate law looks like this. Rate equals K times the concentration of manganate to its order, concentration of oxalate to its order, and the concentration of hydrogen ions to its order. I use a P there rather than a 0 so that we don't mistake it for an actual order number. Okay, so in order to solve the problem, we're going to set up a ratio. What we want to do is ratio in such a way that we get we don't get fractions, we get whole numbers if possible. So we want to put this one on top and this one on the bottom, because with this one on the bottom, we get a ratio of 2 into 8 is 4. So we're going to ratio experiment 2 to experiment 1. And the rate there is 8 for this one, minus 4, and 2 for this one. Now this expression is equal to this one. And this value is going to be 2 times 10 to the minus 3 to the n value. This one is going to be the same k. That doesn't change. And this one's going to be 1 times 10 to the minus 3 to the same power. And then we get these, which are exactly the same. 1.0 times 10 to the minus 3 to the m, and 1.0 times 10 to the minus 3 to the m. And then we have the hydrogen ions to the p's. Oops. Let me put the numbers in there. There should be a 1 and a 1. Okay, so we've taken experiment 2, the data from experiment 2 in this one, experiment from data 1 in this one, and we ratio them. Right? So what we notice is that these are exactly the same. Right? Denominator, numerator, it cancels. Denominator, numerator, cancels. K is the same as K, cancels. So now we bring down this one, 8 divided by 2 is 4. And this one is that one divided by that one to the n power. Remember, if you have a to the n divided by b to the n, that's the same as a divided by b to the n power. Right? So 2 divided by 1 is 2 to the n power. That means n equals 2. So now we can change this to 2. Right? Okay. Next, we're going to have a different ratio. Right? We're going to have K here. We're going to have values here. Right? For this one, actually, let me leave that there and pull this one out and this one out. Leave that one alone. For this one, we want the oxalate to change and the others not. So these two stay the same, these two stay the same, and that allows this one to change. So that means we need experiment 3 divided by experiment 2. And the rates for 3 would be 1.6 times 10 to the minus 3. And 2 would be 8 times 10 to the minus 4. And the values here between these two are both 2 times 10 to the minus 3 and 2 times 10 to the minus 3. This one is going to be 2 divided by 1. And that one's going to be 1 divided by 1. Okay? So these cancel. Those two cancel. These don't cancel. Right? But they do equal to 2 to the m power. And what is 8? Notice if we change this to minus 4, this number becomes 16. So 8 into 16 is 2. So m must be 1. Okay, now we got this one. M is equal to 1. Right. The last one, we want to let the hydrogen ions vary. So it's between this one and that one. So this is going to be 4 divided by 3. Okay, now we need rates. The rate for 4 is 1.6. times 10 to the minus 3, 1.6 times 10 to the minus 3 for that one also. K is going to be the same. The value for manganate is not going to change, 2 and 2. The value for oxalate is going to be 2 divided by 2. And then the value here is going to be 2 divided by 1, right? 2 divided by 1. So these cancel, and we get here is equal to 1. And we have here 2 to the p power. P must be equal to 0. So this reaction is 0 order with respect to hydrogen ion concentration. All right? So if this is 0, what does that law actually look like? If that's 0 power, that value is actually 1. So what we have is the rate equals K times the concentration of manganate to the second power times the concentration of oxalate, 2, to the first power, and the hydrogen ion term drops out because it's equal to 1. Okay? That's how you do initial rates. Oops, I forgot to calculate K. Okay, let's calculate K. In order to calculate K, all you need is this expression, rate equals this, and we take any one of these, plug in the value for rate, plug in the associated value for this term, and solve for K. So in this case, if we take the first one, concentration is 2 times 10 to the minus 4 squared. And this one is, oops, sorry. Actually, I was using this one. That's okay, we can use this one right here. Should work for any one of them. All right, so that one will be 2. This one will be 1 times 10 to the minus 3 to the first power equals the rate of 8 times 10 to the minus 4. So we just need to solve for K. All right, we'll square this value, divide it into that one. Take that one, divide it into that quotient, and that's equal to K. All right, so let's, I'm gonna put 8 exponent 4, put it in my calculator. Then I'm gonna square this one. 2 exponent 4, change the sign, and square it. And then divide it into this value. And then divide by 1 exponent to the minus 3. So we get 2. Did something wrong. Hold on a second. 2 exponent 4, change the sign. Let's square that. Okay. And times 1 exponent 3. Okay. And then divide that into 8 exponent 4. 2, I put something in here wrong somehow or other. Because it's not coming out 2 times 10 to the 5th. Hold on. Oh. Not minus 4. It's minus 3. Then we solve it, and K equals 2 times 10 to the 5th. 10 to the 5th, not minus 5th. There we go. So that would be our K value right here. All right. So that's the method of initial rates. I know it's a lot of work. It's not difficult. You just have to stay organized and look for the ratios that will allow only one to vary at a time. Before I erase that top one, let me see what's coming up. We might need it. Okay, this goes back to what I mentioned earlier, right in here. What's happening in there? Most chemical reactions occur in a series of elementary steps. Two, of course. If it's less than two, then it's the same as the overall. So it's two or more steps. In the process, usually an intermediate product is formed, and that intermediate product then enters into a subsequent reaction, and it disappears. Right? Intermediates cannot appear in the final balanced equation. So in that respect, it's difficult to determine what the intermediate is because you don't see it coming out of the reaction. If you have the technology, you may be able to identify it in real time, but it's difficult. So much of this is speculation, propose multiple mechanisms and say which ones are impossible and then which ones are best satisfy the data. That's where we're headed. Okay, here's an example. All right, I won't need this one then. For this example, we have nitrogen dioxide, carbon monoxide react to form nitrogen monoxide and carbon dioxide. So notice in the first step, you have two nitrogen dioxides react. Nitrogen is blue, oxygen's red. So we have those two funny looking figures reacting to produce nitrogen trioxide plus nitrogen monoxide. So what you're seeing is this intermediate and one of the products, right? This is nitrogen monoxide. Then the intermediate reacts with carbon monoxide and regenerates a nitrogen dioxide plus the carbon dioxide that is also a product. So this is a product, that's a product. This intermediate is created and then used up. And we used two nitrogen dioxides in the first step, but now we've recreated one of them. So if you look at it that way, as step one and step two, step one has nitrogen dioxide plus another nitrogen dioxide yields nitrogen trioxide plus nitrogen monoxide. And then the second step, we take this one over here plus carbon monoxide, and we produce carbon dioxide, plus we regenerate the NO2. So the first rule of a mechanism is that the elementary steps must add together to the overall equation. So let's see if it does. Okay. Let's pull them all down first. NO2 plus NO2 plus NO3 plus CO yields NO3 plus NO plus NO2 plus CO2. Okay. Now, if we've got the same terms on both sides of the equation, they cancel. Right? So we've got an NO here, we've got an NO2 here, it cancels with that. We've got an NO3 intermediate, it cancels with that. And that leaves us with NO2 plus carbon monoxide yields in nitrogen monoxide plus carbon dioxide. Now, is that the overall equation? Yes. So this mechanism satisfies that first rule. All right, we'll come back to that in a minute. Notice what we have in this mechanism is there are two species, two reactants, this one and that one. This is known as a bimolecular reaction because there are two species that collide. And this is, on the elementary step, a second order reaction. Remember I said the overall reaction does not give us any information about the order of the overall reaction, of order of the overall reaction and its reactants. But the elementary steps do give us that information. If we have two species coming together, that's bimolecular, and it's a second order reaction. If we only have one species in the elementary step, and it becomes something else, doesn't matter what the products are, but if it's the only reactant, that's unimolecular, and it's a first order reaction. The termolecular is where you have three components coming together, A, B, and C, yield products. This elementary step is extremely rare. If it occurs, and if we can justify using it in our elementary steps, then it's a third order reaction. But it's very rare for this reason. These species have to come together, first of all, with enough energy to drive the reaction at that elementary step. Second, more importantly, they have to come oriented correctly. All three of them must meet at the same time and properly oriented so that bonds break and new bonds are formed. And that is a very rare occurrence. So we only use termolecular steps, elementary steps, when there's no other option. All right. When we have these several steps, we'll have step one, step two, we have step three. And we know that their relative speeds, rates of reaction for the intermediate steps are in this relationship. This one's very slow. This one's fast relative to each other, right? It may take hours to complete, but relative to each other, this one's very slow and this one's fast relative to that one, and this one is only slow. The one that determines the rate of the reaction is the bottleneck, this one. So the overall rate of the rate of the overall reaction is determined by that one. I haven't seen any where the reaction rates for two of the steps are exactly the same. There's always one that's the slowest. Okay, and we can use this slowest step. We can take that elementary step and derive the overall rate expression. An example would be best. There's the first rule. The sum of the elementary steps must add up to the overall balanced equation for the reaction. If it doesn't meet that requirement, then you throw it out. And the mechanism must agree with the experimentally determined rate law. So if we determine a certain rate law for the overall reaction, and then we derive a rate law from the elementary steps, with this being the rate determining step, and they agree, that's good evidence that we have a valid mechanism. All right, here's another example. Dinitrogen pentoxide breaks down into nitrogen dioxide and oxygen. And these are the 3 steps that are given. All right, we're going to base our calculation of the overall rate law on the slowest step. NO2 plus NO3 yields NO plus O2 plus NO2. All right. First of all, we have to add them together. Sometimes you have to manipulate them, right? And use acceptable procedures. In this case, step 1 needs to be multiplied by 2. Why? Because we need 2 dinitrogen pentoxides. That way we can cancel 2 NO3s from the first step and the other NO3s from the second and third step. We can also cancel the NO2s from either side of the second step and NOs from either side of the second and third step, respectively. Then if we add them together, we get the overall reaction. All right. Let's use this one. Let's use this proposed theoretical reaction and its elementary steps to derive the rate law. Right? We know the overall rate law is, the overall reaction is A plus 2B yields C. Okay? And the proposed steps are these. Step 1 is A plus B yields D. And that is identified as a fast equilibrium. That is, as fast as the D is produced, it goes back to A and B. It's very fast. Fast equilibrium. Now we haven't talked about equilibrium yet. That comes in the next chapter. But for argument's sake, there is a rate constant for that direction, and there's a rate constant for the reverse direction. Okay? And they're not necessarily the same, but the process is very fast, which means it comes to equilibrium very quickly, and now the balance, you can't tell that there's a change in A plus B or D on either side. Once you reach equilibrium, then the amounts of each one, the concentrations of each one are stable. Then the slow step is this one. D plus B yields C. And this one also has a rate constant. Okay? So for this balanced equation, we start with the slow step. Right? This is slow. It's the rate determining step. So we can use the coefficients here to write a rate law for this elementary step. So what would that be? Well, the rate equals first order in D, right? Coefficient 1. First order in B with K sub 2 as the rate constant. Okay? Now, what's wrong with this picture? Let's see, I think I've got that in the slide. Well, I skipped a step. Add these together. Do they add up to that one? We got 1A, we got 2 B's, and we got a C, and the D's cancel. So we met the first condition. I just didn't explain it. All right. So now we can go to the next. All right. So this is our starting point. This is the rate determining step. But where's the problem? The problem is that our overall rate law cannot include D. It is an intermediate. We got to get rid of D. So here's how we do it. Right? D is not a reactant. So we go to the fast equilibrium, and we notice that if we write a rate law for this side of the equation going that direction, let's see, let's move this back over here. If we write a rate law for this one going that direction, the rate would be equal to K1 AB, right? And the rate for the reverse reaction going from D the other direction would be the rate equals K to the minus 1 D. Now, the important part is this is an equilibrium. And we'll learn in chapter 13 that equilibrium is based upon reaction rates. Once you've established that the rate of the forward reaction equals the rate of the reverse reaction, you have equilibrium. So we're going to say this rate is equal to that rate. That means this expression is equal to this expression. Okay? Now, we have a term here. We can solve that equation for D and insert it in here. And that gets rid of D. So we're going to take this equation and we're going to solve it for D. Right? That equals K1 over K minus 1 times A times B. Right, did I do that right? Keep the D over here, move the K1 over here, and A and B. So now we're going to take this and substitute it in here like that. So now the rate equals K2, K1 over K minus 1, and A times B, and then times B again. Okay? What's this? That's a constant. So all these together equal a constant. This term is to the first power, and this one is to the second power. So now we have a rate law with only the reactants in it. Now, the fact that this 2 shows up down here is coincidental. We cannot claim that one was derived from the other. This was derived from the elementary steps only. It's purely coincidental. All right, there it is in black and white. All right, and okay, it's in agreement. All right. See if I can get this finished before I run out of time. All right, we have a theory that governs the reaction rates. And it's called the collision theory. And it has a model. This collision model, actually, this is derived from the kinetic molecular theory of gases, and then it's modified to accompany liquids and solids. But the collision model is based upon the kinetic molecular theory. First of all, molecules must collide. If they don't collide, they can't react. That's the first condition. And for each collision, there is an activation energy, a minimum amount of energy required for the reaction to proceed from reactants to products. That's usually determined by actually the kinetic energy of the molecules when they collide. We don't know yet if there's enough energy there. So the way you increase that amount of energy is increase the temperature. So the temperature is a controlling factor for the reaction to meet this activation energy. And then the last requirement we've mentioned before is orientation. If the molecules are not oriented properly, say they come together with enough energy, but they're not oriented. They have to be this way in order to react. If they're this way, they just bounce off. No reaction. All right. So this activation energy is the energy that must be overcome. And this is what it looks like in a diagram. This is reaction progress. And this one is potential energy. Of all of the components at any one time. So if we have reactants at this level here, this is all the reactants energy. And then you have a collision. They have to meet this minimum amount of energy right here at that top in order for the reaction to proceed. And at this point, we have a transition state, I think your book calls it. Transition state, where bonds are beginning to be broken and reformed, but not completely. Sometimes we call this the activated complex. And if it meets this energy amount and just a smidge more, then it can roll over the top and come down to products. This is the potential energy of the products. Okay? So the activation energy is between here and there. That's the activation energy. Now, what's the difference between here and here? Well, it's a change in energy. Or for our purposes, it's enthalpy. Right? And if delta H is negative in this case, the energy has decreased, then we have an exothermic reaction. All right. And I've already said that. Now, a mathematical understanding of this process was proposed by I think he's Swedish, Svante Arrhenius. And he came up with this equation where a constant value then is equal to this proportionality constant. Oops. There we go. A, and then E, like the natural log E, to the minus activation energy power divided by RT. And you know what R is. R is the ideal gas constant. Only this R has to have energy values in it, joules. So that's why we use 8.3145 instead of 0.08206, which has liter atmospheres in it. This is the one we use in this case. Okay, A is a constant that accounts for frequency of collisions and steric effects. So it has to be empirically determined. But we have access to a modified version of Arrhenius's equation. That's much more useful. This is the linear form of the Arrhenius equation. Right? If we perform an experiment at 2 or more different temperatures, then it will have different K values for each temperature. And if we plot that data versus the inverse of Kelvin temperature, right? So this is Y, this is slope M, this is X, And this is, and that is the y-intercept. So y equals mx plus b will give us, if we plot the temperature in this form against the k's in that form, then we get a line, a straight line. And this is what it looks like for this example. So on the x-axis, we have the reciprocal of temperature in Kelvin. And on the y-axis, we have the natural log of K. And the slope of the line is equal to minus E sub A divided by R. Since R is a constant, then if we have the slope of the line, we can calculate the activation energy for this reaction. All right. So let's see. I got a little bit of room over here. Chemists commonly use a rule of thumb that an increase of 10 degrees Celsius or K for every increase of 10 K in temperature, the rate of the reaction doubles. So what I wanted to find out with this slide, I created this slide myself. What must be the activation energy for this statement to be true? So I had to pick a temperature range. So I picked 25 to 35. That's reasonable. 25 is normal room temperature, and 35 would be a little higher. So that's where we're headed. So first thing I had to do was convert temperatures to Kelvin. So I'm going from 25 to 35, or 298 K to 308 K. Then I set up the expression, and we're going to use the original. It's easier to find the answer this way. Well, it's the way I chose. Let's put it that way. You could probably use this one too. So what we want is to ratio the Ks, because if the reaction rate doubles, the K will double. So that means if we're going from K1 to K2, then K2 is equal to twice K1. Then we ratio K2 to K1. That's this first major step. And that ratios the Arrhenius equations with their respective temperatures. Oops. Then we simplify it. Right? We find that E to this equation is E to this one. When we go from E to this power divided by E to this power, then we say it's E to the power minus the other power. And since this one's a minus, it becomes a plus. Then we factor out E sub A over R and leave the T's behind. Now, what I'm trying to solve for is E sub A. So I have to insert temperature values. And that's on the next slide. So actually what I did was solve for E sub A first, and then I inserted the temperature values and the value for the ideal gas constant. And the end result is that for this rule of thumb to be active, to be valid, the activation energy for the reaction must be 52.9 kilojoules. So that means if the activation energy is different, if it's less or more, then you will not have an exact doubling of the reaction for every increase in 10 degrees. All right, let's talk about catalysts. I'm going to leave that up there. So what is a catalyst? Well, first of all, a catalyst does one thing. It causes the reaction to go faster, speeds up the reaction. Second of all, it participates in the reaction, but it is not consumed by the reaction. In other words, a catalyst comes in one side, goes out the other. Apparently unchanged in the overall reaction. But if we look at the mechanisms, the individual elementary steps, we find that the catalyst is intimately involved with the reaction. It participates. And what it does is it provides an alternate pathway from reactants to products. And that pathway occurs at a much faster rate. Now, for this diagram, what that means is this will be the activation energy uncatalyzed, right, with no catalyst. If we put a catalyst in there, we find that the activation energy decreases. So this would be the activation energy catalyzed. Okay, we just decrease the activation energy. What does that mean? That means for any given temperature with a catalyst, there are more collisions that produce products because now they don't have to meet such a high standard of activation energy to proceed to products, right? And this reaction, the way it's drawn is an endothermic reaction. In other words, the reactants are down here and the products are up here. The concept is the same either way. This is an explanation of what I just described as there are more collisions producing products with a catalyzed reaction. So if we look at the number of collisions with a given energy, we find that as the energy increases to the right, we have most of, for a given temperature, most of the collisions reside in this part, right? And an uncatalyzed reaction means that most of them don't have enough energy, right? Remember, temperature is a measure of the average kinetic energy of all the molecules in the substance. Right? They don't all have the same kinetic energy. It's an average. So some of them will be higher energy, some will be lower, and a lot of them will be kind of in the middle. So this sliver over here shows how many of the collisions actually exceed the activation energy. If we decrease the activation energy and the temperature is the same, then now we have more collisions. The activation energy moves further to one side, and that encompasses more collisions that can produce products. All right. We characterize catalysts in terms of their phase. If the catalyst is in a different phase than the reactants, then it's called a heterogeneous catalyst. A good example of that is a catalytic converter in your automobile exhaust. It has, there's a picture on the next slide. I'll get to it in a minute. In fact, let's do it now. The catalyst is a solid, right? It's platinum and palladium, which are deposited on this ceramic matrix, this honeycomb that's through which the gases flow. And the catalyst is in a solid phase, the reactants are in the gas phase. So what happens is those gases, in order to react, must absorb to the surface in order to react. So here are what we believe to be the steps for a heterogeneous catalyst reaction. We get adsorption, not absorption, adsorption of the reactants to the surface, and they are activated by proximity to the catalyst. In fact, they will migrate on the surface of the catalyst until they find the right orientation and the right catalyst. And then it will produce the intermediate stage, the activated complex or the transition state. When it does that, then you get products formed and they're released. They desorb from the surface. All right. I don't have time to tell you that story, so let's move on. The other type is homogeneous catalysts. These are catalysts that are in the same phase as the reactants. A good example is nature's catalysts, enzymes. Enzymes are biological or biochemical catalysts, but they have several distinctive features that are unique to them versus inorganic catalysts. I think I showed you this one last semester. The Haber-Bosch process, right? This is a gas, and this is with hydrogen, produces ammonia gas. So we need 2 of these and 3 of those. That reaction occurs without a catalyst, but not very fast and not very efficiently. So what Fritz Haber did, well, he did 2 things. He needed higher energy and lots of more collisions. So he did 2 things. He increased the temperature in the reaction vessel, and he increased the pressure, which means there are more molecules in there with opportunities to react. The problem with this reaction is it's exothermic. So if we put the energy term over here, or the delta H, let's be consistent. If we put the enthalpy on that side, then if you increase the temperature, you're going to drive the reaction backwards from an equilibrium standpoint. So what he did was he introduced a catalyst. Solid iron powder. And that caused the reaction to proceed much faster to the product side. So the third thing he did was he took advantage of the difference in boiling points of the reactants and the product. These reactants boil at a much lower temperature than ammonia does. So all he had to do was bleed off some of the contents of the reaction vessel, run them through a cooler, just cold enough to condense the ammonia. The ammonia would drop out as a liquid. And then he would feed the gases back into the reaction chamber. So he was actually extracting that amount from each one and driving the reaction to the right. Okay, so this homogeneous catalyst, actually, I told you that whole story based on a myth. This is not a homogeneous catalyst. This is heterogeneous. Right? If there'd been anybody in the class, you would have opportunity. Well, actually, you're zoomed in. Opportunity to correct me, right? You thought I was talking about a homogeneous catalyst. I wasn't. I was talking about a heterogeneous catalyst. Now, the homogeneous catalyst has to be in the same phase. So here's an example. We're going to decompose hydrogen peroxide, which normally happens very slowly to the 3% hydrogen peroxide in your cabinet, in your medicine cabinet. So after a certain amount of time, it's no good anymore because it's decomposed. But in this case, we're going to speed it up really fast.
Try yours. So that's the technique. Just dump it right in and see what happens.
Oh wow. Okay.
Okay. So
whoa,
we're releasing
okay.
lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got just dump it in really quick.
Okay.
Perfect. Yours is like more. And you just generate tons and tons of oxygen. It's being trapped by the soap, okay? It's like a supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything, if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff.
This is like more of a
Okay. What happened here was potassium iodide in aqueous solution was added to a 30% hydrogen peroxide. Right? It works better with the higher concentration. And then some dishwashing soap and food coloring was added for the foamy colored effect. But what happened was the hydrogen peroxide decomposed at much, much faster rate because of that iodide. This is the proposed mechanism for that decomposition. Notice the slow step for these elementary steps, 1, 2, 3, and 4. The slow step is the first one, where iodide ion combines with hydrogen peroxide and produces this species and that species, this intermediate. And the other steps are fast relative to the first one. But the first one is exceedingly faster than the simple decomposition of hydrogen peroxide. I had a student one time who's was expecting a child, and his partner got an ultrasound. So they knew the gender, and they wanted to do a gender reveal party. So they used this procedure with either blue or red food coloring to reveal the gender of the child. Unfortunately, they got it wrong. They went back for another ultrasound and found it was the other gender. So they had to go back and do it over again. All right. Other types, that was a liquid catalyst, liquid reactant phase. The upcoming phases are all gas. And the problem is the decomposition of ozone into oxygen. Now, at upper altitudes, very high up in the Earth's atmosphere, ultraviolet light converts molecular oxygen into ozone. And ozone is a very, very efficient attenuator for ultraviolet radiation. So once you've got that ozone in the upper layer, it protects the lower layers of the atmosphere from ultraviolet damage. But if you have nitric oxide coming from incomplete combustion, usually from fossil fuels, it migrates into the upper atmosphere and it serves as a catalyst for this reaction, these two elementary steps. The nitrous oxide combines with ozone and produces nitrogen dioxide and oxygen. And then the free radical oxygen combines with NO2 to produce NO and O2. So what the reaction that is overall reaction is this free radical oxygen combining with ozone to produce oxygen. This normally occurs at a slow enough rate so that the sun's radiation can keep the ozone concentration at an acceptable level. But what we're doing is we're speeding up the reaction using this catalyst, the nitric oxide. Okay. Another way that can happen is with Freon. Right? The original Freon, or Freon 12, and we don't have time to talk about the naming conventions for Freons, but the Freon they're talking about here is dichloro-difluoromethane. Migrates into the upper atmosphere, and then under the influence of ultraviolet light from the sun, decomposes and produces this free radical chlorine. Remember, free radicals are any atoms, ions, or molecules that have unpaired electrons. In this example, chlorine. If we draw the Lewis dot structure for chlorine, we find it has that. There's that unpaired electron. And that's the one that does the damage. So this free radical chlorine combines with the ozone, and it comes in one end, it goes out the other. That's the sign of a catalyst. One of the signs. It also has to speed the reaction up. And also degrades ozone into oxygen. All right. So I had a thought. It's escaped me. Oh, I think I go back. No, it's gone. Sorry. So that's the introduction to chapter 12. And now you need to take the review document, work out those problems, and I'll have this is version 2 of the review document. That's the one I'm going to use for our review session next week. And within 24 hours, I hope to have the written worked problems for that version of the review document. I've got them done. I just need to scan them and post them in Brightspace. And then we'll also have a lab, chemical kinetics lab next week. And we don't have time to discuss it right now. So you'll have to go to the videos and get some insight into the procedure calculations. And I will check your notebooks next Monday to see if they're ready to go. Okay. That's it for today.